Wait,
so,
we're doing quantum tunneling.
Yeah,
We gotta say that because...
So, like, basically, the thing that sets quantum mechanics apart from the rest of science, right, is, what they have probability waves. So we have two types of probability waves. We have position probability, waves x, and p, which is momentum, or velocity. Well, we use velocity, but anyways, we have momentum waves and position waves, and those are the two waves that make up. So what we're going to focus on mainly is the position wave. I don't even think we'll need the velocity wave. So hold on, let me grab a quick eraser here. And basically, so all you need to understand about a probability wave is it's like any other wave. It can interfere with itself. It can interfere with other waves. And what a probability wave is, what it'll do, a probability position wave will tell you the probability of finding a said object, we'll say like an electron, for example, in a particular location. So for example, right, what this means is we'll have like a wave like this, right? And the peaks are the highest points of probability. So this might be like 57%, maybe this is more like 30%, etc. And this line here represents 0. Right? Easy enough to understand. They have the ability to constructively and destructively interfere with each other. So if I have a wave like this, and then I have the exact opposite wave down here, right? And we're going to pretend that they're on top of each other, even though they're not. They'll add up to exactly zero, and then the whatever particles will not be found in this location, right? Simple enough. So the thing is this can have some weird and wacky properties, right? So you look at something like, we'll say, for the sake of explanation, we'll pretend for a moment that we have a ball here, right? And it's at the top of a hill.
Okay.
Right? So this ball is in a high energy state. I'm going to kind of rip this from another video. Sort of, not really. Kind of just going to use part of an explanation for metastability. So this ball is going to roll down here, right, into this hill, and then it'll be here, right? Like normally, right, let's say there was, maybe it had some incentive to get over this hill, because down here is an even lower energy state, and all objects want to get to the lowest energy state possible, right? So the ball's sitting down here. Now, normally we'd think, okay, well, the ball is just going to sit in this ditch until the end of time, and that'll be that. It'll just be there forever, ever, and never, ever change unless somebody comes along and kicks it over the hill.
Right.
Quantum mechanics, a little bit different. Now, technically, if we were to put this in terms of wave function, the highest probability for it to be found is in this spot. This is the peak probability. This is the most likely location. It will be here, and in the next second, and in the next second, and in the next second. And that's classical mechanics. It'll always be here forever. But if we pretend this is quantum scale, and this is just an electron sitting on the bottom of a hill, so I don't know, some magnetic hill, it technically has a very small probability of being found on this side of the hill. So even though it technically shouldn't be able to go up and over, instead of going up and over, it's not really moving per se. It's more like it's not existing here anymore and existing here in the next second. It's not really moving. It's not going anywhere. It's not moving from point A to point B. It's just that given enough time, it could appear on this side. Of course, that's not to say that just because you have an infinite amount of time, it will appear on that side.
Right.
Probability is still a very real thing, and we can't just say that because we have an infinite amount of time that this will occur. But as things like this can happen. So, you know, for example, I have a wave functions because I'm made up of quadrillions of particles, and my wave function happens to cancel out so perfectly that I have the highest probability rating of being right here. This is where I am. But I technically do have a very small probability of appearing on that side of the wall. If I keep walking into this wall for an extreme amount of time, much longer than the universe will live, hypothetically, I could appear on the other side of the wall.
Okay.
Not gonna happen because it's such an excruciatingly small thing. But if I had an atom and I toss it at the wall, that chance suddenly gets a lot higher, especially if it's a very simple atom. So that's essentially, in the most basic form I can put it, quantum tunneling. And it can be used for a lot of very useful things. If you can figure out how to get quantum tunneling to work, this is the cool part of science. This is very theoretical stuff. But, you look at how our sun works. Our sun works by, we've got these two protons here, and they really don't want to go together. But gravity's forcing it down so hard that these ones just keep jostling around and getting so hot that they get so close that the strong force takes over and forces them together, right? And that makes a lot of energy. That's very useful for us. But if we could find a way to use quantum tunneling to overcome this initial electric barrier and just have them fuse without putting on a lot of pressure, then you would have unlocked cold fusion and you'd have extreme amounts of energy just flowing all over the planet. This is probably the most realistic form of cold fusion, by the way. So if anybody wants to figure out how to do that, you should get on that.
Okay.
So, yeah.
All right. Quantum tunneling.
Yeah.
All right. Thanks.